All right, my AB kids, we are actually working on section 5.6 today, but I want to take you through kind of the organizer that we made for this whole unit. The last two sections are on 5.6 is on concavity, whichever way you want to say it, and the last section's on the second derivative test, and they're both really linked, but they're also really linked to stuff that we looked at previously in the unit. So remember, we started out with, this was kind of my overview page before we started the unit, and we talked about if you have a function and you want to figure out what are called critical points. That was section 5.2. So critical points come from taking the first derivative, setting it equal to 0, and solving for those values. So that x equals 0, x equals 2, those are called critical points. If I want to take it the next step into section 5.3 and figure out where the original function is increasing or decreasing, then I make a sign chart using those critical points on the sign chart, and I sign chart it with values from the first derivative. So in other words, I take a value like -1. If I plug a -1 into this first derivative, however you want to look at it, into the first derivative, all these three places are all the same first derivatives. But if I put a -1 in there, I get a positive value out. If I put a +1 in there, I get a negative value out. And if I put something like 3 in there, I get a positive value out. So I've now created a sign chart off of the first derivative, which then tells me where I'm increasing or decreasing with the original function. So positives are increasing, negatives are decreasing. And that's based off of where the first derivative is positive or negative. Then I can tell also from the first derivative test in section 5.4 where I have maximums and minimums, because if you think about it, if it's increasing and then decreasing, I've created a maximum. If I'm decreasing and then increasing, I've created a minimum. So I can tell from the sign chart where I have maximums and minimums. That's my first derivative test. Section 5.5 added one more thing on, a maximum or minimum value, which is different than the actual maximum or minimum locations within your graph. This is the highest y value or the lowest y value. And what happens is you have to find your critical points where you have maximums and minimums, but then they also give you endpoints. They give you a bounded region that you're looking at. And because of that, you need to check the endpoints too to see if maybe the endpoints might be your maximum y value or minimum y value. Then you get into this thing called concavity. Now before I go there, let me take what we've done so far and let's see if we can draw a graph of this thing. Get a general idea of what the original function was. So a couple of things that might be of interest to us. First thing is, right from the original, the x-intercepts, where it crosses the x-axis. Where does y equal 0? 0 equals x squared and x minus 3. I can see that x equals 0 and x equals 3 would be those places, x-intercepts. Well, x-intercepts are where it crosses the x-axis. So 0, 1, 2, 3. Now, if I check out the work that we did over here, see how down here at the bottom, I have a maximum at x equals 0 and a minimum at x equals 2. So maybe they might be points that I'd be interested in as well. If x is 0 or if x is 2, what are the corresponding y values? Because that's going to give me where those point locations, the coordinate locations of my maximum and minimum. Now I'm putting them back into the original function all the way at the top. 0 squared, 0 minus 3. Multiply them together, I still get 0. So I have a maximum at 0, 0. If I put a 2 in here, 2 squared is 4. 2 minus 3 is a -1. 4 times -1 is a -4. That tells me that I have a minimum. So right here is a maximum, and at 2, -4, I have a minimum. Put it all together. I know I'm increasing from -infinity to 0. Then I am decreasing from 0 to 2. And then I'm increasing for the rest of the graph. So just with those kind of pieces, with those few locations, I can graph this whole function what the original one was. We don't have a maximum value or a minimum value because I haven't blocked off a portion of the graph. I'm just looking at the entire graph. But let's go to this thing called concavity. Concavity, if I go back to my picture up here, concavity is where it changes from a happy face to a sad face, or a sad face to a happy face. In other words, all the way till about here, that would be an area that's concave down. And then it switches. It switches somewhere in this location over here, and now it turns, oh, I'm happy for the whole rest of the graph. And so this guy over here would be a situation of concave up. Where it changes right here, that's called a point of inflection. So where it changes from concave down to concave up, or if it were the other way around, concave up to concave down, that creates what's called a point of inflection. Well, all of this stuff comes off of the second derivative. And so the second derivative is the one that decides concavity, where it's concave up or concave down. So let me show you. If I get to the second derivative on this, we already know what the first derivative is. We said that the first derivative, in fact, I'll write it one more time, and you have this from up above. The first derivative was 3x squared minus 6x. Well, if I take that and I go now to the second derivative, 6x minus 6, to find the concavity, I set that equal to 0, solve for x, so I get x equals 1. I create a sign chart for the second derivative. So I take a number to the left of 1, like 0. That gives me negative. I take a number to the right of 1, like 2. That gives me a positive. And since it's changed signs, I know I have a point of inflection at x equals 1. And I also know from my sign chart it is concave down from negative infinity to 1, and concave up from 1 to infinity, because my sign chart says that. Okay? Now let's check the graph out. Let's see if that's really true for what we came up with. Up here, I am concave down from negative infinity to 1. At 1, it changes from concave down to concave up, point of inflection, and then it's concave up from 1 to infinity. And so I can see that all lines up with what we just calculated using the second derivative. Now here's what's interesting about the second derivative test. If I think about something that is concave up, concave up's like a happy face, right? If it's a happy face, this is concave up. What does that create as far as an extrema? Is it a maximum or is it a minimum? If I'm concave up, then I've created a minimum. And if I'm concave down, oh so sad, concave down, then that creates a maximum. So it's another way, a different way, an additional way for you to be able to tell if you've got maximums or minimums. So back in section 5.4, you used the first derivative to determine if there are maximums and minimums. And now in section 5.7, they're saying, hey, you can also use the second derivative. Sometimes that's easier to figure out if they have a maximum or minimum. Okay, that's the overview for this particular section. Let's check it out. Determining concavity, here it is. And you'll hear me say, funny enough, it's concave sometimes I say, concavity, sometimes it's whatever. You'll hear me switch back and forth between them. So, concavity, as soon as you see that word, think second derivative. All right, what does it look like to be concave up? Concave up is very happy. There it is, concave up. What does it look like to be concave down? Oh, so sad. If a function is concave up like a parabola, what's the derivative, first derivative doing? I'm looking at y equals x squared, right? That's my parabola. And I can tell all of this area right here is when my function is decreasing. Decreasing means my first derivative is negative, less than 0. Then I get to this place right here. Well, what's my first derivative now? It's just equal to 0. And then as I come on the other side here, now my function is increasing. And if my function's increasing, then I know my first derivative has to be positive. All right, so how does this relate? If my function is concave up, then the first derivative is increasing. And if it's concave down, then the first derivative is decreasing. Which leads to the following thing about concavity. If I am a positive second derivative, my function is concave up. And if I'm a second derivative that's negative, my function is concave down. So looking at the sine graph keeps changing all the time. It goes, this would be concave up, then it goes concave down. This would be concave up, and then it goes concave down, and it keeps switching back and forth between the two things. Here's concave down. All right, I'll just label it one time. This is concave up, then it goes concave down. Then it goes concave up, concave down. So it can switch within the graph. Each of these locations here, where it changes from one to the other, they're all considered points of inflection. Now let me take a moment. Points of inflection are different than critical points in that critical points, they don't have to change signs. You can have a sign chart that has a critical point that goes negative, positive, 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 and all of the values on your sign chart are still called critical points regardless of if the sign changes or not. Where points of inflection, it has to change signs. If you had a sign chart that went negative, positive, 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 you would only have one point of inflection at that location where it went from negative to positive. Where it goes positive, positive is not considered a point of inflection. So it literally has to change signs. So something good to note. And we're going to talk about that at the bubble at the bottom. All right, so find the intervals of concavity. Concavity, second derivative. Got to find the second derivative. Well, got to go through the first derivative first to get there. So find the first derivative. I end up 4 comes down times 1/4, knock each other out. I got an x cubed. I have minus a 12x, and then I have a plus 1. And thankfully they didn't make me have to solve that, because if I set that equal to 0 and solved it, that would not be pretty. It doesn't factor or do anything nice like that. But I don't have to worry about that because I really am just concerned about the second derivative, and hopefully that will be more friendly. So 3x squared minus 12 is way better to set equal to 0 to solve for x. Now you're on a journey to try to find the points of inflection. If I take a 3 out, x squared minus 4, when I set it equal to 0, 3 equals 0 doesn't do anything, it just gets knocked out. So I get x values of plus or minus 2. Well, I create a sign chart. Negative 2, positive 2. I start checking values. Now remember, this is into my second derivative. It's a sign chart for the second derivative. So I'm going to take values to the left of negative 2, like negative 3. Negative 3 squared is 9, times 3 is 27, minus 12 gives me a positive. If I put a 0 in, something between them gives me a negative. And if I put a positive 3 in, I get a positive value out. So it's just a matter of plugging in to your second derivative. Now, can you say intervals of concavity? Absolutely you can. Read your sign chart. You know it's concave up from negative infinity to negative 2. And then it goes concave down from negative 2 to 2. And then it goes concave up again from 2 to infinity. If they asked you for justification, which they didn't necessarily, but we can do it so you can see, because the second derivative, concave up, is positive, and this one will be because your second derivative is negative, concave down. So points of inflection for this one. Points of inflections, I'm going to call them POIs, because that's a lot to write. Points of inflection. There's a point of inflection at f of f at x equals c if f of c is defined and f double prime, second derivative, changes signs. And this is what I was saying to you that's really significant. That Points of inflection have to change signs at that value. If they don't, they're not called points of inflection. So in other words, a point of inflection is where the graph changes concavity All right, so we actually have, if I went back up here, look at my sign chart, it changed at -2, therefore x equals -2 is a point of inflection. It changed at +2, therefore x equals 2 is a point of inflection. Both of those actually came out to be points of inflection. All right, if I flip the page, now I'm looking at some common mistakes that are made with these things. So the common mistake when finding a point of inflection, find my notes here. Here it is. Get it where so you can see it. Two common mistakes when finding points of inflection. Assuming that the second derivative, just because the second derivative equals 0, means that there's a point of inflection. And also assuming that just because the second derivative does not equal 0 means there's no point of inflection. Just because of those things, you can't automatically assume it's a point of inflection. Easiest way to do it is make a sign chart and make sure that the signs change at that particular location. So now they're going to give you the graph of the first derivative. Now it's very important what you're looking at to answer the question, knowing what graph you're looking at. The first derivative graph, when we get to number 3, that's the second derivative. So given the graph of the first derivative, find the points of inflection and state the intervals of concavity. They're giving you the first derivative and they're asking you a question about its derivative. It's all based on the second derivative to get these points of inflection and concavity. So if I'm given the first derivative and I'm asked questions about what's the second derivative doing, then I need to be concerned about the slopes of this graph. I'm not concerned about above the x-axis, below the x-axis, because I'm going from one derivative to the next derivative, which means I'm concerned about the slopes. That's how I'm going to define where it's concave up and concave down. So concave up, and I don't have both, concave down, and then we'll talk points of inflection. Well, what are the slopes, first of all, in this first segment that goes from -4 to -1, all of my slopes would be negative slopes. So it is concave down, -4 to -1. Then I have positive slopes. Well, my slopes are positive between -1 and 1. There's concave up. Negative slopes between 1 and 2, concave down. Oop, positive 1 and 2. And then from 2 to 3, I am back to concave up. Where did the slopes change signs? That's going to be my points of inflection. First place, it went from negative to positive is at x equals -1. It went from positive to negative at x equals 1. And it went from negative to positive at 2. And so those are your points of inflection for this one. But what you're looking at changes for number 3. Number 3, now they're giving you the second derivative. And if they're giving you the second derivative graph, then that means you're looking at what's above the x-axis versus below the x-axis to be able to determine this one. So I am looking at still, I've got places where it's concave, concave up, if I were writing that correctly. And then I've got places where it's concave down. Where are they? Above the x-axis, from -infinity, see the arrow, to -3. So above the x-axis, -infinity to -3. Below the x-axis, from -3 to 1, concave down. Above the x-axis, from 1 to 3. Below the x-axis, from 3 to infinity. Where did it change signs? Where did it cross the x-axis? Positive to negative at x equals -3. Negative to positive at x equals 1. Positive to negative at x equals +3. And so there you go, points of inflection. So it just changes. Watch what they give you, and then determine from there what you're looking for. So if you're looking at the first derivative and asked about the second derivative, you need to know slopes. If you are given the second derivative and asked, it's just above the x-axis versus below the x-axis. All right, example number 4, last example. Does the line tangent to the graph of this function at x equals 1 lie above or below the graph of f? Now, if I think about how concavity works, if I am concave up, I'll give you a quick picture on the side here, concave down, and I'm thinking about tangent lines to the curve. So the tangent lines, if I'm concave up, like say here, all of my tangent lines are going to be concave up. My tangent lines are going to be below the curve. No matter where I put them, they're still all going to be below the curve. Where if I'm concave down, see my tangent line now? My tangent lines are going to be above that curve. And that's what the question is asking you. If I have this function, what are my tangent lines doing? Are my tangent lines above or below that curve? And so I'm concerned about concavity. That means I need to get to the second derivative. So let's try. Here's my function, original function. I want to know what the second derivative is. Well, the first derivative, this is a product rule. So I've got to product rule it. I will have x times, first times derivative of the second. Well, the derivative of e to the negative x is a negative e to the negative x. So I'm just going to put that negative in the front. Plus the second, e to the negative x, times the derivative of the first, which is a 1. So when I put this together to be able to solve it out for the second derivative, actually maybe I'll just put it here, I have a negative x e to the negative x, and I have a plus e to the negative x. And I need to now derivative that to get to the second derivative, right? Well, the first piece is going to be a product rule again. The first, negative x times the derivative of the second. Now the derivative of the second is a negative e to the negative x. The negative e to the negative x is going to make this positive e to the negative x. It was a negative negative. First times the derivative of the second plus the second e to the negative x times the derivative of the first is a negative 1 this time, and then plus the derivative of e to the x, which is a negative e to the negative x. That's all a hot mess. Let's see if we can clean it up just a touch. I have x e to the negative x, negative 1, so minus e to the negative x, minus another e to the negative x. What is x that we're concerned about? It is a 1. F double prime of 1. So put a 1 in. 1 e to the negative 1 minus e to the negative 1 minus e to the negative 1. Cancel these first two, positive, negative, and I get negative e to the negative 1, which is negative 1 over e. Now, the second derivative came out to be a negative response. Because it's negative, that means it's concave down. Negative second derivative means concave down. And if I'm concave down, then I can tell all my tangent lines are going to be above it. So to answer their question, I'm going to say, therefore, the tangent lines are above the function because let's say at x equals 1 the function is concave down. Something like that, something in that neighborhood is what you want to say. Okay, we're going to look at a couple examples and see where that takes us. So the first one that I want to look at is number 2 from the practice. We started this one in class, but then we got interrupted because the the bell was going to ring and we were trying to do it too fast. So let's try again. So I have, the question says, find the points of inflection for the function. So I got to go for the second derivative. So I'm going to work my way to the second derivative. Here it goes. The derivative of sine is cosine. So I have the cosine of x over 2, but then it's times the derivative of the angle. So this is like a 1/2 x. So it's times 1/2. I'm going to put the 1/2 in front. There's my first derivative. Second derivative, I'm going to take 1/2. Derivative of cosine is negative sine, same angle, times the derivative of the angle. So that when I solve this guy out, I end up with negative 1/2 times 1/2 is 1/4 the sine of x over 2. Points of inflection. Set the second derivative equal to 0. Here it goes. 0 equals negative 1/4 the sine of x over 2. Divide by the negative 1/4, so now you're at 0 equals the sine of x over 2. Well, you kind of have to go on a journey a little bit to be able to figure this out. You want to know where the original sine, I'm going to come over in this box because I'm out of space over there a bit. I want to know where this regular old sine of x equals 0. So I think about my unit circle, and the first place where the y value is 0 is at x equals 0. And if I keep going, the next place is at pi, right? So I've got x equals 0, x equals pi. If I were to go, check out my domain here, if I were to go the other way, it would also be x equals negative pi, right? And then I could go x equals 2 pi, and I can keep going around and around and around because I'm thinking about I've got to have values between negative pi and 3 pi. So I'm going to stop there for a minute. But that's not what I have. What I have is the sine of x over 2 equals 0. So I have to take each of these things, x over 2 equals 0, x over 2 equals pi, x over 2 equals negative pi, x over 2 equals 2 pi. And what I'm going to do is figure out what they are for this particular situation by multiplying everybody by 2. X over 2 times 2 gives me x. So this one, and 0 times 2 is still 0. This guy, when I multiply by 2, gives me x equals 2 pi. This guy gives me x equals negative 2 pi. This guy gives me x equals 4 pi. So go back to your domain, and we're going to eliminate ones that don't fit. If I look between negative 2 pi, or negative pi and 3 pi, then the ones that I want, 0's in there, 2 pi's in there, negative 2 pi's not. Negative 2 pi would be to the left of this, and positive 4 pi would be out of this too. So these two I eliminate. So I'm going to set up a sign chart. My sign chart is a little interesting this time because I know I have 0 on there, and I know I have 2 pi on there. But I have boundaries this time, where in number 3 you don't have boundaries. This time they gave me boundaries. My left boundary is negative pi, and my right boundary is 3 pi. So I'm setting up my sign chart based off of this. All right, so I need a value between 0 and negative pi, so maybe you might want to take negative pi over 2. And I'm going to plug that into the second derivative. So is the sine of, if I were to take the sine of, say, negative pi over 2, I end up over here, negative pi over 2. You have to think of the y value. What's the y value at negative pi over 2? And it turns out it's going to be negative. Negative times a negative makes this a positive. If I put in a value like positive pi over 2, well, now that's a positive value. This is a negative value. This is going to be negative. If I take something beyond 2 pi, maybe I might take, I don't know, 3 pi over 2 or no, 5 pi over 2. And that would then give me, same idea, I'd have a negative times a negative, and that gives me a positive over here. So the question's asking, find the points of inflection. It has to change signs. So if I change signs, then I know that I have a point of inflection at x, is it x? Yeah, x equals 0. And I know I have a point of inflection when it goes negative to positive at 2 pi. If they had asked you for concave up, concave down, you could say it's concave up from negative pi. Here's where the boundaries come in. From negative pi to 0. It is concave down from 0 to 2 pi, and then concave up from 2 pi to 3 pi. So these boundaries will come into play if they ask you a question like that, even though they didn't. All right, let me just give you a quick overview of some of the practice problems. The rest of these are all the same thing. Find the points of inflection, so create a sign chart based off of the second derivative, and then determine where it changes signs. The second part, 6 and 7, state the intervals of concavity. Same question, find the second derivative. You can tell from the sign chart where it's positive, it's concave up, and where it's negative, it's concave down. So that takes care of those two questions. Then it asks you about the graphs. Now realize the first set of pictures, 8, 9, and 10, they're asking you from the first derivative graph, they want to know where are the points of inflection. You're looking for changes in slope. Where the second questions, 11, 12, and 13, finding points of inflection is above the x-axis, below the x-axis. We talked about that earlier. Again, 14 and 15, do the tangent lines lie above or below the graph? Find the second derivative. If the second derivative is positive, it is concave up. All the tangent lines are below. If the second derivative is negative, it's concave down. All the tangent lines would be above. And so that's pretty much the summary of, and then I think there's some test prep questions at the end. But there you go, section 5-6. Shoot me an email if you have any questions, and I'll see you in class.